Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to pop open the lid on a brand new topic. I am talking, of course, about thermodynamics. I really like this topic a lot, and I'm very excited to be discussing it with you. And so without further ado, I present to you Thermodynamics Volume 1. As always, your feedback is more than welcome and highly encouraged, so please feel free to drop your thoughts in the chat if you're watching this live, and if you're watching this as a video, please feel free to leave me a comment, because without your feedback, I am lost. So, one of the reasons why I like thermodynamics so much is because, if you think about it, right, you go to school, you read books, you study for tests and this and that. What are you learning? You're learning all about the who and the what and the when and the where and the how. But thermodynamics gives us one of the rare opportunities to address the question, why? Why do things happen? Why do physical and chemical changes occur in the first place, right? It's a very interesting question. I'm sure you've probably been riding in a car with a little kid at some point, and the kid's like, hey, why does it rain? And then, the water, it kind of just, it builds up in the clouds, and it gets too heavy, and it collapses, and so we get rainfall. Oh, well, why does the water evaporate from the ground? And you can just keep asking the question why over and over again infinitely. So we're not going to put the final nail in the coffin to answer the question of why physical and chemical changes occur. But I think with an understanding of thermodynamics, we can dig a little bit deeper and just kind of climb up a few rungs on that ladder of why, if that makes sense. So that's what we're going to talk about with thermodynamics. Why do physical and chemical changes occur? What is the driving force that drives physical and chemical processes? Very good question. In order to do that, we need to define some terms. One of the most important things that we'll learn about, it's called spontaneity. So what is spontaneity? Spontaneity is like something that you'll see on a dating app or something. Like you look up a profile, oh, I'm really spontaneous. It's like, what does that even mean? Anyway, so in the context of thermodynamics, what spontaneity means, we're talking about spontaneous and non-spontaneous processes. A spontaneous process in thermodynamics is a process that occurs without ongoing outside intervention, right? You leave it alone and it occurs spontaneously. By contrast, a non-spontaneous process is one that does not occur without ongoing outside intervention. There must be some sort of intervention, some sort of energy input into that system in order to get that process to occur. So that's what we're talking about, is what makes things spontaneous versus non-spontaneous, and are some processes that are spontaneous more spontaneous than others, and how would we understand and quantify all of these relationships? So, when it comes to spontaneity, we all have an intuitive understanding of spontaneity, at least in terms of physical or mechanical systems. Sorry, I don't know why I said symptoms. Anyway, so take gravity, for instance, right? So here we have an image of a young man holding up an apple, right? So when you're holding up an apple, you're holding that apple up, and it's in a system of high potential energy, and if it were on the ground, it would have a much lower potential energy, which is why when you release the barrier that holds the apple up, it spontaneously falls down. Mechanical systems, such as this gravitational system here, they proceed in a direction that minimizes potential energy. Whenever there is a lower potential energy situation possible, this system will proceed in that direction on its own, right? So we all understand this on an intuitive level, but what we may not understand is the direction of spontaneous or non-spontaneous chemical reactions. So here we have an image, two images, both of the same statue, the Statue of Liberty. One of them was in 1886. I think that's about a decade or so after the Statue of Liberty was built. And then over here on the right is a more present-day image of the Statue of Liberty from 2018. So this statue, it used to be like this bronzy sort of color, and it spontaneously turned green. And that was a chemical reaction. It's an oxidation reaction, right? So it oxidized from this copper bronzy color to green. So it's not very obvious in this situation why this happened, right? What is the driving force behind this? It was kind of easy to understand the whole apple falling down to minimize potential energy, but how does the Statue of Liberty turning from bronze to green, how does that minimize potential energy? What's going on? So in other words, what we are looking for is something called a chemical potential, right? A chemical potential. We're looking for a property that helps us predict the direction of chemical change. And so that's what we're going to talk about in this stream, and of course in several streams that follow in this thermodynamics live stream series, right? A chemical potential, that's what we're looking for. One thing I wanted to point out is that the spontaneity of a process is much different from the speed of a process. So a few live stream series ago, we were talking all about chemical kinetics, which is concerned with the speed of chemical reactions, how fast they occur. But let's not be confused, and let's not falsely equate speed with spontaneity. For instance, the reaction of diamond, right, which is just an allotrope of carbon, into graphite, which is another allotrope of carbon, is a thermodynamically spontaneous process. It happens without any ongoing outside intervention. However, if you have any diamonds, they're not going to be turning into graphite anytime soon, because this is a very, 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 very slow process kinetically, right? So when it comes to spontaneity, what we're looking at is sort of like the difference in potential or chemical potential between like the final and the initial state. In this case, the final state would be like graphite, the initial state would be like diamond, right? But when it comes to kinetics, we're looking at the thermodynamics of those like little individual intermediate states that govern the speed of the reaction. So it's very, very important that we are able to differentiate between spontaneity and speed of a chemical reaction. So one thing I wanted to revisit is the first law of thermodynamics, and I think before I do that, I just want to sort of cut away from the PowerPoint here and show you guys something. So this is, let's see if I got it, hang on. So this is a playlist that I made way back in the day, all about thermochemistry. It's my thermochemistry playlist. I'll put a link to it down in the description. And I think a lot of the stuff that we discuss here in this thermochemistry playlist is very good. It kind of develops a good foundation upon which you can build and understand the content of these live streams that are going on right now. So we talk about all the way from what is thermochemistry to the first law of thermodynamics. We talk about state versus path functions, how to calculate work, how to calculate heat. Talk about a couple of different forms of calorimetry. We talk about enthalpy, which is a property that we're going to talk about in a few minutes. Endothermic and exothermic, just all this different thermochemistry stuff. So I would highly recommend viewing that content if you're confused about any of the stuff that we're going to talk about tonight, because a lot of that stuff is sort of defined and discussed in that playlist. So that's my thermochemistry playlist. So let me go back to the PowerPoint for the moment. So yeah, we're going to revisit the first law of thermodynamics. So at this stage in your chemistry education, you should know something about the first law of thermodynamics, but in case you don't, we're going to go ahead and re-examine it right now. So according to the first law of thermodynamics, the total energy of the universe is constant, right? It's that whole quote about, there ain't no such thing as a free lunch, right? And that is true in the context of thermodynamics, right? Energy is neither created nor destroyed. Whatever energy you can harness to do some work for some process that you want to happen, that energy cannot be created out of nowhere. It must have come from somewhere else in the universe. Now, this is a little bit of an oversimplification, right? It's really not necessarily energy of the universe that's constant. It's really mass energy, right? Because mass and energy are related according to that famous equation, E equals mc squared. But for simplicity, let's just say that total energy in the universe is constant, and that'll be simple enough for the purposes of what we need to do here. So another thing that we learned with the first law of thermodynamics is that we usually consider the universe as comprised of two components, which we call the system and the surroundings. So the system in thermodynamics is defined as the part of the universe that's under study. It's the part of the universe that we're looking at. And the surroundings would be everything else, literally everything else in the entire universe. And another thing that's important to understand about thermodynamics and system and surroundings and all that is the sign convention that is nearly universally adopted by chemists everywhere. So what I mean by sign convention is like what is positive and what is negative, right? Got a message from Sean Chani. Says, yo, what up, Ben? Not much. How are you? Good to have you in here. Thank you for joining me. And I hope you like thermodynamics, because we're going to talk a lot about it tonight and in the next several streams that follow. Okay, so sign convention. What does that mean? What is positive? What is negative? So the way that we assign positive and negative signs to processes that happen thermodynamically is if something is being done on the system by the surroundings, in other words, if the system is like absorbing energy from the surroundings, then we consider that change a positive change. So if it's being done on the system, then it's positive. Conversely, if the energy is flowing out of the system and the surroundings are gaining energy from the system, then that is considered a negative. That will carry a negative sign, right? That will carry a negative sign. So if it's being done on the system, it's positive. If it's being done on the surroundings by the system, then it's considered negative, whether that's internal energy or work or heat or enthalpy or whatever we're talking about. So got a question, says, can we do Vesper theory? It's only me in here right now. I will refer you to some videos on Vesper theory. I actually have a couple of videos on them. So if you stick around, I will send you those links. But for now, we're going to stick with thermodynamics because that's the topic of the stream. And also, when I do these streams, I record them as videos and then publish them so that people can view them later. So unfortunately, no, I'm not going to switch topics right now, but I do appreciate your question, and I will be happy to refer you to all of the content that I have on Vesper theory. It's also a very, very good topic. Okay, so we know that anything that's being done on the system is positive. Anything that's being done on the surroundings by the system is considered negative. And that's going to be very, very important to help our understanding going forward. So another thing that I'd like to do is I'd like to revisit the property known as enthalpy. So again, if you're this far in your chemistry education where you're talking about thermodynamics and spontaneity, you should understand what enthalpy is, but in case you don't, I'll go ahead and sort of redefine it. So enthalpy, which has the symbol H, go figure, no idea why, is equivalent to the sum of the internal energy and the product of pressure and volume. So we get this equation H is equal to E plus PV, right? And under conditions of constant pressure, enthalpy is actually equal to just the heat, because at constant pressure there's no work being done, it's all heat. So I actually have a video called What is Enthalpy, where I go through this derivation. So I start with this equation of enthalpy up here, and I derive the equation down here where we get that enthalpy is equal to the heat absorbed or released by a system under conditions of constant pressure. So we have enthalpy. So what I'm getting at with this is that enthalpy might be the first place that we go when we are searching for a chemical potential, right? We're searching for a property that gives us a criteria for the spontaneity of a process, whether or not it will occur without ongoing outside intervention, right? And so just to look at enthalpy one more time, just to talk about enthalpy a little more. So if the change in enthalpy, if delta H is negative, we call that process exothermic. That means heat is being released into the surroundings. So if you have a chemical reaction taking place in a flask or a beaker and you feel the flask and it gets warm, or if it gets hot, that would be an exothermic chemical reaction. And then on the flip side, if delta H is positive, that's an endothermic process, and that is one in which heat is being absorbed by the system. It's taking in energy from the surroundings, and if you had an endothermic reaction going on in a beaker and you felt it, it would actually be cool or cold to the touch, right? So we know what enthalpy is, we know what exothermic means, we know what endothermic means. So we might be thinking to ourselves, okay, maybe enthalpy is a criterion for spontaneity. Maybe enthalpy is the chemical potential that we are looking for. Now, if this was the case, then all exothermic reactions would be spontaneous and all endothermic reactions would be non-spontaneous. However, this is actually, unfortunately, not true. There are several examples of processes that are endothermic. They absorb energy from their surroundings, and yet they are also spontaneous. So for instance, ice melting anytime your external temperature is greater than 0 degrees Celsius, that is an example of an endothermic process that happens spontaneously, right? Liquid water evaporating into water vapor, right? If you're looking around, if it's just rained a couple days ago and you see puddles on the ground, those puddles are evaporating into the air. That's an endothermic process, but it also happens spontaneously. Another example is sodium chloride. If you dissolve it in water, sodium chloride has an endothermic heat of solution. It absorbs energy from its surroundings, and yet it dissolves in water spontaneously. And so enthalpy cannot be a chemical potential. And enthalpy cannot be a criterion for spontaneity. There must be some other property that we can define and describe that is a criteria for the spontaneity of a process. And that property is called entropy. Not to be confused with enthalpy because they sound similar, but entropy is the property that we're looking at here. This is the property that is the criteria for spontaneity, and it has the symbol S. I'm assuming that's because E was taken by internal energy. But let's go ahead and define entropy real quick. Entropy is a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. So basically what that means is that the more energetically equivalent ways that you have to arrange the components of a system, the higher the entropy will be. It will have a higher value when there's more energetically equivalent ways to arrange the components of the system. And a simpler definition of entropy is simply a measure of disorder or randomness, right? So we all kind of have like an intuitive understanding of entropy, at least on a macro level, right? We understand that disorder and randomness is something that occurs spontaneously, right? What happens when you go 6 months without cleaning your room, right? Things start to get messy, things start to get disorderly, dust starts to collect. If it's my house, dog hair, lots of dog hair starts to collect, and this all happens spontaneously, right? My room is never going to just clean itself, right? To clean my room would be non-spontaneous. That would be something that requires an ongoing outside intervention. And just, I forgot to mention this earlier, but just because something is non-spontaneous doesn't mean that it is impossible, right? Non-spontaneous processes occur all the time. It just means that you need to put some energy into it to get it done. You need to couple it with a spontaneous process, with a highly spontaneous process usually. So that's what entropy is. So here's an equation that was developed by Ludwig Boltzmann. This equation is actually scribed on Boltzmann's tombstone, interestingly enough, a little fun fact there, and that is S is equal to K times the natural logarithm of W, right? Where K is the Boltzmann constant, which is 1.38 times 10 to the minus 23 joules per Kelvin, and then W is simply the number of energetically equivalent ways to arrange the components of the system, right? So W doesn't have any units to it, right? Because it's just a number. And so the units of entropy are joules per Kelvin. Now, these units of joules per Kelvin, it's going to be very, very significant that we understand that going forward. But for now, we can just sort of leave this equation as is. S equals K ln Q, right? Entropy is something called a state function. So once again, I refer back to my thermochemistry playlist. One of the videos within that playlist was called state functions versus path functions or something like that. We talk about what a state function is. So a state function is basically a property whose value only depends on the current state of that system, not how the system arrived at that state. So anything that is considered a state function, the calculations are actually pretty easy because to calculate the change, the delta of a state function, all you have to do is to take the difference between the final and initial states. And so we arrive at this equation right here where we have delta S, the change in entropy, is equal to the final entropy, S final, minus the initial entropy, which is shown here as S initial. Got a question from Yash Agarwal. It says, is this part of chapter 5 of AP Chem? I think that depends on what book you're reading, sir. I don't think all chapter 5s are created equally. But yeah, this is just, I think this is like chapter 17 of my general chemistry textbook. So what chapter it is, I don't know. Depends on what book you're reading, right? All right, so entropy is a state function. So the change in enthalpy is just simply the final entropy minus the initial entropy. So to demonstrate entropy a little bit more, I want to imagine a situation in which we have this sort of system right here. So this is like two flasks that are sort of connected by a stopcock, and the stopcock is currently in the closed position. And let's say we have 4 atoms of a gas in the flask on the left, and we have no atoms of gas. It's a vacuum. We have nothing in the flask on the right. So what do you think is going to happen when we open that stopcock, right? Where there's several possibilities, several energetically equivalent possibilities of how these atoms could be arranged within this 2-flask system once we open that stopcock. But for the moment, let's imagine that we have 2 sort of macro states that could be possible. One, which we'll call state A, is the state in which all 4 of these atoms remain in the flask that's on the left-hand side. And then we have state B, which is a situation in which 2 atoms are in the left-hand flask and 2 atoms are in the right-hand flask, right? Now, there are more possibilities, but for the time being, we're just going to consider these 2, right? And so entropy would drive the arrangement of these gas particles into one of these states, but not the other. And we're going to sort of figure out why. So when it comes to state A, right, in which all 4 atoms are in the flask on the left-hand side, well, there's only one possibility, right? And I've numbered the atoms 1, 2, 3, and 4, right? So the question is, how many microstates can give rise to a macro state? In this case, state A, there's only one microstate that can give rise to this macro state, right? All 4 atoms on the left-hand side, on the flask that's on the left-hand side. That's the only way that we can get this state in this system here, right? Now, the other one, state B, in which 2 atoms are on the left flask and 2 atoms are on the right flask, well, we have 6 possibilities, right? We have 6 energetically equivalent ways to arrange the 4 gas atoms such that 2 of them are on the left-hand side and 1 of them is on the right-hand side, right? We can have atoms 1 and 2 on the left, 3 and 4 on the right, 1 and 3 on the left, 2 and 4 on the right, 1 and 4 on the left, 2 and 3 on the right, 2 and 3 on the left, 1 and 4 on the right, 2 and 4 on the left, 1 and 3 on the right, and 3 and 4 on the left, and 1 and 2 on the right. That's a lot of energetically equivalent ways to arrange these atoms, especially compared to the first possibility where the only way to have 4 atoms on one side is to have all 4 atoms on one side. There's no other possible way to arrange the components to achieve that state. Now, I'm sure you can imagine as the number of atoms increases, the number of energetically equivalent ways to arrange those atoms such that the same number of them are on either side of the flask goes up dramatically. So if you have like 10 atoms, then you get like way more possibilities, right? So this is basically what we're talking about when we're talking about entropy. So the question is, well, where would this system go? Like, what would happen once we open up that stopcock? Well, what would happen would be that this system would proceed in a direction that leans closer to state B. Why? Because this state has more entropy. There are more energetically equivalent ways to arrange the components of this state than there are the previous one where we only had 4 atoms on one of those flasks, right? So that is entropy, and that is actually going to do it for me tonight. I just wanted to introduce the concept of thermodynamics, spontaneity, spontaneous, non-spontaneous, chemical potential. We talked about enthalpy, right? And we kind of ruled out enthalpy as a chemical potential because there's a lot of endothermic processes that occur spontaneously. And then finally, we defined entropy, right? So entropy, that is the driving force of chemical change. And we're going to talk about this in much, much more detail in the streams that follow. Next week, we're going to talk about the second law of thermodynamics. So we talked about the first law. Next week, we're talking about the second law of thermodynamics, in which we will see that for any spontaneous process, the entropy of the universe increases. All right, guys, so that is going to do it. Thank you very much for watching. Kind of a short stream tonight, but I didn't want to overload you with too much information. So if you want to stay tuned for the next stream, that's going to be next Sunday. So that will be November 21st. We will be here live, 9 o'clock p.m. Eastern Standard Time. And I really look forward to seeing you guys then. All right, take care.